Okay, so this question is about a balloon that's been with a mass attached, and it has been released from just under the surface of the water. Okay, there we go, it's released as they fall through the water. So all of this is going down through the water. Okay, first question is to find the terminal velocity. Now the terminal velocity is given by this plateau here, this horizontal portion to the line. Okay, so we need to look over on the y-axis. You can see that this is 9 here, and there's 5 squares between 8 and 9. So each square must be worth 0.2. So that means that the terminal velocity is 8.2 meters per second. All right, we need to talk about ideas of forces, right? So we've got the mass hanging underneath this balloon here. Okay, now this is almost exactly the same answer as the skydiver, the traditional skydiver question, but they're seeing, can you apply what you know about a skydiver to a new and novel situation? All right. So at the beginning, when the balloon first starts to fall, the largest force on it is the weight of the mass in the balloon. Okay, and at the beginning, there's going to be zero water resistance because the balloon's not yet moving through the water. Okay, but if you imagine putting your hand into some water, dipping your hand into a bath or something like that, when you're not moving, there's no water resistance against your hand. As you start to move your hand backwards and forwards in the bath, okay, then you can feel the water pushing back on your hand, right? And you could use the word drag for that, or you could use the word water resistance for that. Okay, so you can see that the balloon, as I've drawn it at the moment, that the water resistance, that the weight is greater than the water resistance, right? Okay, and what that means is that there's going to be a resultant force downwards. Okay, there's the resultant force. Okay, and because there's a resultant force, that means that there's going to be an acceleration, and it's going to be in the direction of the resultant force, which is of course downwards. Right. As it accelerates downwards, then the water resistance arrow is going to get longer and longer, right? Okay, until it's the same length as the weight arrow. Okay, when the weight and the water resistance are equal to each other, then that means that the resultant force is zero. Okay, and then that means that the acceleration is 0, and that's what we call terminal velocity. State the pressure linking pressure difference. Okay, so it's a difference, so we need a delta in there. It's a lowercase p. That's important because uppercase P is power. Okay, and then it's rho times by g times by, well, actually it should be delta H, shouldn't it? Because it's the change in depth. Okay, the increase in pressure of the balloon. Okay, so we're just going to do the substitution into this. Okay, the density of water is given in kilograms per meter cubed. That's great. Those are the units that we need, so no need to do any conversions or anything. G, it says on the front of the paper, is 10 meters per second squared, or 10 newtons per kilogram. Okay, and then the change in height, so the depth, is 25 meters, right? So if you multiply all of that together, you should get 250,000 pascals. Now, if you imagine, like this is the pressure that we've got from these 25 meters of water here, right? So this 250,000 pascals comes from the depth of the water, but on top of the water, we've also got some pressure as well, and that's caused by the pressure at the surface, which is this 1 times 10 to the 5 pascals. Now they've given it you in standard form, okay, but don't allow that to freak you out. 1 times 10 to the 5 pascals is the same as 100,000 pascals, okay, and you're going to take that and you're going to add it to the pressure from the depth of the water, okay, and then that's going to give you 350,000 pascals all right, which is 3.5 times 10 to the 5. Okay. Now in this one, it's giving you the pressure and it's giving you the volume, right? And then it's asking you for the volume at this depth. But you can see, look, we've just calculated the pressure at that depth. So what you know is the question tells you P1 and V1, and it's asking you, it tells you P2, and it's asking you to calculate V2, right? So this is the formula that we need to use. Okay, and then this is 1 times by 10 to the 5 times by 0.46. Okay, and then the pressure at depth was 3.5 times 10 to the 5, okay, times by V2. Okay, I've got 10 to the 5 on each side, so I can just cancel those out. All right, and that means that V2 is going to be equal to 0.46 divided by 3.5. Okay, and if you do that on a calculator, all right, then it'll get you 0.1314. Okay, but again, same as always, we need to look back at the question. You can see that here, that's 2 decimal places. Here, that's 2 decimal places. Okay, here, that's 2 decimal places. Okay, so, sorry, not 2 decimal places, my bad. 2 significant figures is what I meant to say. So you can see that we should be giving our answer to 2 significant figures, which is 0.13 meters cubed.